A game like rock, paper, scissors is a two-person zero sum. Before we do, we need to establish this theorem. We're looking at two-person games, so we're looking at two-dimensional functions. This is always true. Take the supremum of both sides in the other component. The left-hand side is now a fixed number, and so the infimum is bigger than that lower bound. Von Neumann showed that if you view the function as a function of the first component only, and it's concave, it's convex in the second, then you have equality. So let's run through it again, because this kind of sequence is game theory. If I take the inf, it's smaller. I'll take the sup of both sides and the other variable, and then take the infimum again. So von Neumann's conditions, it's concave in the first, convex in the second, means that if I look at this function, where I'm looking at the infimum of all the second component pieces, and then think it as a function of the first, it looks concave, and vice versa. And that looks convex. To guarantee that it has this kind of shape, you need a compact domain so that you ensure your supremums are maximums and your infimums are minimums. You're not looking at infinities or edge cases. This is a surprisingly hard proof. We won't do it because it's beyond the scope of our prereqs, but these three conditions enforce a saddle point existence. There's a couple different proofs of it. The more modern proofs use fixed point theorems to show it. Instead, we'll just kind of examine it. So we have a saddle point, so that means we have these two graphs we can look at. At the saddle point, it's a max one direction, min the other direction. And we'll use that point as our handoff. Y0 is the minimum y value. Which is then less than or equal to the maximum over the first component. And vice versa. It's the maximum x value for that fixed y, which is then bigger than or equal to the minimum y value. And there's the opposite inequality. Let's do an example to kind of finish things off. This will be the way game theory works, is the way we're going to do this construction with just a finite number of points. First step, I'll minimize in y. So for every x value, I pick the minimum y value, giving me a function of x. Now I'll maximize an x. For the right-hand side, I am picking the maximum x for every y. Now I've got a function of y, and I minimize over the y's. 3. 2 less than 3. There's our strict inequality. If I enforce that f is linear, plus 2 plus 3, that's a plus 5. And we'll run through the construction again. Minimize in y. For every x, I'll pick the smallest y value. And then I'll pick the biggest of the x values. For every y, I'll pick the biggest x value. And then I'll pick the smallest of those y's. Equality, because linear is both concave and convex. Zero sum, one person wins, only the other person loses. We'll play the Robin Hood game. Robin Hood is going to take from the merchants, depending on what path through the forest, and the merchants are going to lose to Robin Hood, depending on their path through the forest. Put in the payoff. These are our F values. F is the money that the merchants lose, and it's also the money that Robin Hood gains. And now we go through the procedure. I want to minimize my losses. Depending on what action Robin Hood takes, I want to minimize my losses. Robin Hood will look to maximize that. 2 is my expected. Robin Hood wants to maximize his gains, so he runs through the cases that the merchants could take. And he knows that the merchants are going to minimize his gains. Putting it together, both of them go to the north path. Let's change the payout matrix a little bit and run through the procedure again. Minimize my losses depending on what path I take, and then maximize. Well, the other way, maximize my payout depending on the path they take, and they'll want to minimize that. Putting it together, now we have a strict inequality, and pure strategies will no longer give a clear answer. If we modify the game to have multiple trials, then we can start looking at a mixed strategy. Take a probability that you go down north or south path and look at the losses in each case for Robin Hood's location. And the idea is I would like then to make his choice indifferent. No matter what he does, I have the same losses. Solving for the probability. Go through the same for the other player with Robin Hood's location. Look at the gains depending on what path the merchant takes. And I'd like the merchant's minimization to be indifferent, that no matter what he picks, I'll have the same gain. Solve for the probability. And put both strategies into place simultaneously. The losses for the merchant are the same as the gains for Robin Hood. This is known as the Nash equilibrium, and it's the best strategy they can do. Since it makes the inequality sharp.